briefing. I always hope that this thing works when I start, especially today. So we're going to go on with the Linux lecture. As Prashant said, there will be an email with instructions for people who could not make it to class today. So you do not worry, you'll get all the information. We'll do our best to make this work. So last time when we started talking about Linux, we have covered basically roughly 4 chapters in the book. The one was the introduction, or these were like the first 2 introduction chapters. Then we covered also process management, and we covered the process scheduling in Linux. These were not very different in many ways from what you have studied in Linux. We have also hinted that there is data structures, kernel data structures that you can use in Linux, and we have basically, we didn't go through them, but we just mentioned some of those that are there, like double linked list and so on. So today we're going to build on what we have covered. The first part of the lecture might be a little bit redundant in some sense because the syscalls is basically very similar in many ways. Some very many changes between the Linux and Linux differences. But then we're going to take it much deeper dive into the interrupt handling mechanism that you have not covered in Linux almost. I mean, you have just touched upon it. And then we are going to actually talk about top halves and bottom halves. So system calls in Linux is basically the only interface between the user and the actual kernel. Okay, so there is no way. It's not like in Linux where you have like the servers and so on. That the only way between you and to go from user space to kernel space as a user is via system calls. Okay, it's a single common layer between the user and the kernel. Almost everybody now strives to be compliant with POSIX. Linux tries to be compliant also with another standard SUSV, the single Unix specification. Linux has been trying to minimize the number of system calls as much as they can. And there are reasons for that. We're going to quickly go through them. All system calls in Linux need to return a type long. Okay. Each system call has a number, just like Linux. Nothing earth-shattering. I'm going to try to move this. You have, it's basically, it's mostly architecture dependent because there are lots of things that requires understanding the architecture. So you have them in the sys underscore table where you have all the entries for the syscall. Now the difference between, one of the major differences between Linux and Linux is that Linux had system calls per server, right? So each server had implemented its own system calls and exposed it to the users. In Linux, you do not have that. You just have whatever the number is today, number of system calls, and they're all implemented sort of like in the same table. I mean, they're all defined in the same table, not implemented in the same table. And the call stack is very similar. So you go from the user space where you have you call print on C or Python or something. That talks to basically a library, usually in C library, where you call the print in the C library, and the print in the C library actually calls write in the C library. Write basically writes to a device, and write basically has one-to-one mapping to system call. So you go then to the kernel mode. Okay. System call definition. This is how you define the system call. Syscall underscore define 0. Okay, 0 here means that you're having zero parameters. Okay, and for example, basically this is a system call that returns task ID. Okay, virtual number of the task. So this is, you don't need any parameters for this. You just need the get PID. Basically, it's the get PID system call. You don't need any parameters for that. Get PID of your current process data. Okay? And each system call has a defined handler, very similar to Minix, where you actually have the handler is actually what does the actual work. Okay? The way that system calls work in Linux is that system call results in an interrupt. They actually result in an exception, but people use the two terms interchangeably. As we are going to say in a couple of slides, interrupts in Linux are basically hardware interrupts. They need to be coming from the source, should be hardware device. So it causes an exception or a trap, and the control is switched to the kernel space. Okay? You have a certain number that is defined for the exception for system calls on Linux, and that's 128. Okay, that's the interrupt number. So all system calls have this interrupt number. Once you go there, okay, then you start basically looking at the input, at the parameters of your system call to actually know what system call are you actually using. Okay? The system call handler for the general system call handler that actually takes that system call is called system underscore call. This is where you actually try to go to the different system calls that you have. It's architecture dependent, obviously. On x86, this system call is actually implemented in entry_64.s. It's assembly code. Okay, so it actually tries to go and read registers and stuff. You pass the actual kernel to the actual kernel, the system call number via the EAX register, one of the general registers in x86. That's how you actually pass the number. Okay, and this is done in user space. So basically, part of what your compiler does, or your compiled language does, or if you have an interpreted language, part of what is being done is that you have the library, the system call library, basically changing the EX register to actually go to the correct system call number. How to implement a system call in Linux? This is actually a link to a pretty recent tutorial, because this has changed over the years, and basically this is from 2019, so it will work. Okay, it's a little bit different compared to Minix, but not a whole lot different. So now, why not implement a system call? So you guys have implemented a system call as part of your lab one, right? But there are many reasons for you never to implement an actual system call in Linux, and in Minix if it ever picks up and becomes a system that everybody uses, right? So first of all, you need a system call number, and that number, well, if it's my own kernel, if it's my own kernel version, if I'm changing my own kernel, then I can just like add some number and I'm happy. But then if you actually want to implement a system call that actually does anything, so if you're a hardware company trying to add a system call to the Linux to the main Linux kernel, okay, you cannot just like go on GitHub and push your changes and say, okay, I just added a system call with number 500. It doesn't work that way. So you need basically somebody to assign that to you, and that usually is quite hard. The other reason is that once you have system call, you don't remove a system call. Do you know why?
Backwards compatibility.
Exactly, backwards compatibility. You cannot just basically start adding system calls in random and decide that, oh, I'm just removing them. Okay, and that's one of the main reasons that Linux tries to keep its system calls to a real absolute low number, compared to Windows, which actually has thousands of system calls. Okay, so you don't want to break user space applications in the coming 10 years. Now, each architecture needs to separately register the system call and support it. One of the main reasons that we run on Linux is that it's architecture independent. It runs almost on anything. So if you have a small device or a large device, you want your code to run basically without caring about the architecture. So you run Linux on Raspberry Pis, but you run it also on the big fat servers. You run it on some microsystems, and you know it covers everything, right? So if you change one number somewhere in some architecture, you want to make sure that you can have that same system call available for all other architectures, which is a pain. Okay. And basically, system calls are not easily used from script. So I mean, now you have added your system call. It's not like the system call exists in nowhere. You actually needed to add it to some language library, right? Like the C library. Otherwise, it's completely useless. Nobody's going to code in system calls, right? Basically, maintenance becomes an issue because you have the numbers, and basically, the system call is almost always an overkill for anything that you're going to do. So, in reality, nobody implements system calls, except in labs. Okay? The other alternative is to actually build what is called the Linux kernel module. We'll talk about that later. It's basically the Linux way of actually adding servers, sort of. It's not for adding servers, but it's for basically extending the kernel with some modularity, some form of modularity, where you actually hook up code to the kernel using a simple command line that is modproc, basically, without even touching the internal kernel code. Okay? So that's something that we are hoping to be able to cover, hopefully. Okay? Now to the main meat of this lecture, and that's basically interrupts and interrupt handlers. Okay? So why interrupts? Basically, you have these very fast running chips, processors, basically, that can run hundreds of millions of instructions, or millions of instructions in a second, right? Or in a very short time, you have this very enormous capability. Most hardware does not run at the same clock speed of the processor, right? So you want to be able to basically make the processor talk to all the other very slow devices. And that way is basically interrupts. There are actually two ways to do it. One of them is using interrupts, the other one is using pulling. Most hardware that exists on Earth works with interrupts. Where basically, once the hardware is ready, it sends an electronic signal on the chip to the processor saying that I'm ready, okay? As a hardware. Very few hardware runs with pulling. Pulling basically means that your processor will, every some designated time units, go and ask the hardware if there's something ready for it. Okay, if there's something for the hardware to actually process. Okay? So, the good thing about interrupts is that it enables hardware to signal to the processor. So you have the keyboard, you have the mouse, you have your memory chip. All of these things, they're way slower compared to the processor, your network, and so on. So you have this way of making each card, every peripheral, everything, basically pull or interrupt the processor and tell it that there's something ready now for it. The hardware then does not need to. We don't need to try to synchronize between the different hardware chips, right? Because that would be awful. Basically, trying to synchronize two computers, two processors, is already a hard thing. Now, trying to synchronize your entire computer with 100 subsystems, it's just never going to work. So everything works asynchronous now. Electronic signals going from hardware to hardware to hardware in the processor. That is basically called the interrupt controller. The interrupt controller is a very simple chip, electronic chip that basically has a vector table, has a table that basically says that if I get a signal on this pin, then it's this. If I get a signal on that pin, it's that. So it's a very simple circuit, actually. So it's and that chip enables the processor to basically talk to all kinds of hardware that the processor knows it exists, or that the processor does not know it ever existed. So in many cases, you have a laptop, you have a computer, and then there's this nice piece of equipment that comes out new, right? And it's basically something that was not there when your computer was made, but still you can actually run it on your computer via USB or using something different. So each interrupt will have unique number, unique value. Now take this with a grain of salt, because in reality not each interrupt has a number, and that's a huge part of this lecture. And these interrupt values are often called the interrupt requests, or IRQs. Okay, the IRQ lines is basically
slide that the software is like very slow as compared to the hardware, and that's why we sort of do the poll rather than the push. So, but like, why is it the case? Like,
no, the hardware, most hardware is much slower than the processor.
Oh.
Right? If you continue pulling, if you basically sit down and have your processor every 5 milliseconds go and pull the keyboard, did he type anything? Then maybe I'm not typing like I'm doing right now, and then the processor has to do context switching, because if it's pulling, then it needs to go and ask something about something.
Oh.
Right? So it needs to ask the keyboard if I'm typing right now, which I'm not. Right? So it wastes processor resources. That's why you want interrupts that basically push notifications to the processor. Okay? So each IRQ line is assigned a number, a value. Okay. IRQ 0, the number 0 is the timer interrupt, which is basically your clock, your CPU clock. IRQ 1 is the keyboard interrupt. So it goes like that. I mean, there are a bunch of numbers. Okay. Unlike syscalls, not all IRQ numbers are defined. So you have basically a range of IRQ numbers that are just not defined. Okay. There's just like some number that gets assigned dynamically to different hardware, and this enables basically the processor or your computer to talk to any hardware. Because if we have a number assigned to each interrupt, then I have already defined that this number is for the keyboard, that number is for the memory, that number is for the mouse. But then there are 10,000 types of mice now that each one of them, many of them require very specialized drivers, because they have all sorts of different buttons that do all sorts of weird things. You have 10,000 keyboard layouts, you have Chinese keyboards, you have Arabic keyboards, you have Hebrew keyboards. So I mean, you cannot just like define everything right away. You need to actually have the system get updated with the drivers. And another example is that interrupts associated with the devices on the PCI bus are dynamically assigned. So you have a PCI bus, and you have basically a range for the PCI bus components that you're going to connect. The important notion is that a specific interrupt is going to be associated with a specific device, and we'll see how this is done. So the difference between interrupts and exceptions, I sort of said that already. Basic interrupts are hardware, exceptions are software. So when you have syscalls, that's a software, right? Most people would just call everything interrupts. So interrupt handlers. The concept is very similar to the syscall handler. Okay, each interrupt, each device generates an interrupt that is basically associated to an interrupt handler. So you need to, and that's basically your device driver. So that is actually what you're doing when you install new device drivers. You're just teaching your processor how to handle the interrupts. Okay, besides all the other things, right? But the device driver is in essence that. basically, this enables the processor to again communicate with any device, but enables you also to basically update the drivers easily. Because now what you're going to try to do when you get a new hardware is that you're going to install the new driver, but then if you want to update it, you should just be able to update the interrupt handler, basically telling the processor that now this is what is needed to be done. Device drivers can be implemented as in the kernel. Many of them are, but also can be implemented as an LKM, a Linux kernel module. Interrupt handlers are written in C, so they are not assembly. There is an interface obviously with assembly, but interrupt handlers in general are just C. They run in a special kernel context, which is called the interrupt context. It's different from the user context, from the process context. It's different from the kernel context. It's an interrupt context. Okay? The handler is atomic and thus cannot block. So you want your entire handler to just run from the beginning to the end. Alright? And thus, this must be very quick, because if you have something that is atomic running in the kernel, that basically means that, you know what, a device driver that goes haywire can just like make your entire computer not reply to anything, because you know it's very slow. It's non-blocking and very slow. And even if your device driver works very well, but you still have things such as a 10 gig internet card that just produces a lot of data packets that needs processing and requires copying and requires all sorts of things, and then all of a sudden you have the faster now devices, like the NIC cards, can actually hog your entire processor. So the Linux way of actually solving that is that all device drivers are divided into two halves. The top half and the bottom half, which sounds very, intuitive, right? So the top half is basically the first part of the interrupt handler, and it is the real interrupt handler that the kernel deals with. And this should be basically things that you absolutely need to do, right? Everything that you absolutely do not need to do right now can wait. So basically, you run an interrupt handler upon receipt, okay? And it's non-blocking, so it just run until it's done. And you perform only time-critical work. Time-critical work should be that you act the sending device that you have received the interrupt, so you're going to process it, and that you basically reset the hardware so that you can receive a new interrupt on that same pin. Because otherwise, if you do not reset your hardware, then all interrupts. So if you're typing and I type, and my interrupted handler does not actually handle that, then I cannot type anymore until basically the hardware is reset. The bottom half, you do the rest of everything. Okay? So let's go to the network. Yeah.
Is acknowledgement only a time critical process, or?
Sorry?
In the previous slide, it is given that acknowledgement on receiving the interrupt, right?
Yes.
So is that only the time critical process? Is there something else also which happens?
There can be other things that are time critical. We'll actually give examples.
Okay.
Okay. So there can be other things, and we'll actually say when you should use what, when you should put your code in the bottom half, and when you should put it in the top half. So that's. So basically, you have a network card that receives packets from the network. Okay. Then the first thing that you should do is that you alert the kernel of the availability of these packets via an interrupt, basically. Now the kernel responds by executing the registered interrupt for the NIC, for the network card. The interrupt runs, so the interrupt handler runs and acts to the NIC that, okay, I'm processing this data, and now this is what you were asking about. So in this case, the network interface card, it has a network buffer, right? A hardware network buffer. if you do not copy the data from that network buffer to your memory, then what is going to happen is that you're going to overflow the buffer. So once you receive that interrupt, then it's time critical for you to actually empty the buffer, move and copy everything into the main memory, so that basically you can receive more network packets. Okay.
Does this only work with copying the data without blocking because the network card has direct memory access?
That works because exactly. So because you have direct memory access, so now that's exactly why we're saying that this can be in the background. Obviously, if you do not have direct memory access, which is like a very essential thing now for most computers to actually perform, then you're sort of screwed because you have to wait until everything gets copied. Otherwise, you lose the data. So it works actually partially because of the direct memory access. Yeah. Okay. So basically, the kernel now, when you have an interrupt, your interrupt handler acts, copies data, or gives the order to copy data, and just doesn't do anything after that. And then it's done. It clears the hardware, and you can overwrite the whatever is in the buffer right now. Okay. There are new things when it comes to network. There's something that's called DPDK, which basically tries to even circumvent going through the kernel whenever you receive data, because you have DMA, because you have direct memory access. DPDK, what it tries to do is basically tries to minimize even the kernel requirement to handle this interrupt. It just like goes magically into the main memory. Okay. So each device is associated with one driver. Okay. Each interrupt-based driver registers one handler only, and I have interrupt-based because if you have a polling-based system, for some reason, very few components work with polling for different reasons. But basically, almost all the things that you deal with registers and interrupt handler. Okay. On success, and this is basically done using something that's called request_IRQ, defined in /Linux/interrupt.h. Okay, where most of the definitions for interrupt handling is done. And on success, the request IRQ returns 0, basically saying that, okay, I have registered this interrupt handler to the kernel now, so now the device can run. Okay? A common error is eBusy, which basically says that your IRQ is already in use, which basically means that, well, this line or this number is already in use. This is how this thing looks like. So you have the request IRQ. You have you define an interrupt number, okay, and then you have some flags. We'll talk about the flags in a little while, and you have a name, okay. You have the actual handler, which is a pointer to the actual code, okay. So for the flags, you have the actual handler that points to the actual code. You have a name for that device, and that's basically if you're logging or if you're looking through your D message, is basically where you have all your logs and stuff. You'll see the name of the device, and then you have something like called dev. We'll talk a little bit about it when we talk about the flags, like next slide. So flags. So I started by telling you that when you have an interrupt, everything gets blocked. In reality, you can't actually control that behavior. So you have a flag, one of the flags that you define when you actually attach a device, when you attach a handler, okay, is the IRQ disabled flag. And that basically instructs the kernel to do one of the two things. If you have it as set, okay, that means that everything, all interrupts are now blocked. Nothing worse. So if you have it set for your device driver for your keyboard, that is basically telling your computers that if you have an interrupt from my keyboard, everything else stops. Nothing waits. Okay? No interrupts occur between when I'm typing and so on. Okay? So for most, and if you have it unset, that means that, well, everything else runs. So my network packet, my network card can basically interrupt my typing, but you know, no two keystrokes will basically override each other. So you only disable interrupts that are like you. So which one do you think is used more? Sorry?
Second one?
Yes, the second one, basically, because you want your computer to work, right? The other one is the IRQF.
Yeah, I actually have a question on this one. What would be an example of like a commonly used device that we have that would use the first one, right? Like most things that I would think of like a network. Like
Timer.
Timer, okay. So the timer is really the only one.
Yeah, I mean, basically things that are that you completely do not want anything to interrupt, and that's basically that. This would be interrupts that are for example, if you, I think also some of the memory interrupts are like that. So there are very few who actually run that way. But here's the thing: you can't actually define that. So basically, if you're writing your own driver, it's up to you to actually set it in whichever way you think. Now, if your driver will be accepted in the main Linux streamline, that's a different thing. Probably people will frown upon it, but yet again, most drivers don't come like in Linux, so you download them from some weird place, right? So if you download some weird drivers from some weird place that nobody has looked at, then the device driver designer decided that I'm setting this to whatever. So I mean, that's why you shouldn't go around and get device drivers from everywhere. The second one is actually interesting, the IRQF timer. And that's basically a flag that tells the system if it can use metadata on this interrupt to actually, as entropy, as basically an input to its random number generator. Basically, there are no true random number generators, but still we need random number generators for all sorts of different security purposes, privacy purposes, including in the kernel, and including in some of the crypto libraries in the kernel. So to get these random numbers, the kernel needs to do something that is more brilliant than just try to use the Python random number generator, which is just crap, right? So what it does is that since interrupts happen at any time of the day, right? When you're designing your device driver, you can actually tell the kernel that, oh, by the way, you can use, for example, the time when my interrupt happened to actually as food for your random number generator. And it can use all sorts of different metadata on the interrupt handler. So this is basically something that you're helping the kernel to be better with. Okay? Now, if your system, for some reason, has interrupts that happen at certain times of the day. Example: some of the systems that do backup. Okay, they start exactly at the same time of the day, every day, right? You should not be setting that for that flag for these systems, because then you're basically messing up your random number generator. The IRQF shared and dev. Dev is actually one of the parameters that we talked about. The IRQF shared is a flag that actually enables different multiple devices. Sir? Oh, yeah. Talking too much. So it enables multiple devices to actually share the same interrupt number. And we'll talk a little bit about shared interrupts later. I actually messed up two things. So the IRQF sample random is the one that's just for random number generator. I'm sorry, it just messed up these two. The other one actually specifies that this handler is for the actual system timer. So it's something that is probably going to be very high priority for the system to run right away. Okay? Sorry about that. So, reentrancy and interrupt handlers. So when one of your interrupts are happening, it basically masks all other interrupts of the same kind, no matter what, how you set the flags. Okay. This is basically to prevent two interrupts of the same kind to override each other. So you wouldn't basically end up having the same interrupt overriding the second, like happening at 2 times after each other, one of them overriding the other. Some interrupts actually require masking all interrupts, as we said. And the same interrupt handler is never invoked concurrently, so you never have it on 2 processors. You have a multi-processor system. You have 2 processors. You're not going to have it happening in parallel in 2 different processors. This basically makes writing interrupts much easier for the kernel, because all of a sudden you don't need, as a driver developer, to think about concurrency issues. So you just know that if the interrupt happens, that interrupt will not happen again until it's done, basically. Okay? So why interrupt sharing? As we said, we have this kind of chip, right? That basically has a certain number of pins, and this is the maximum number of interrupts that you're going to support. Okay? So since you have a limited number of pins, and you have an infinite number of devices that you can attach, then you want a way to be able to actually overbook these pins. And the way that you do that is using interrupt sharing. Okay? And for interrupt sharing to work, you need the hardware to actually support that. So you need the hardware to understand that it is sharing the interrupt handler number. So and you need the software, the kernel basically to know that too. So the way that this works is that once the kernel gets the interrupt number, say 5, say that this is shared between 5 different devices. The kernel should be able to go and pull each of these devices to check which one is raising that interrupt. So you need hardware support that enables the kernel to actually pull the device if it has raised an interrupt or not. It's a very simple modification in terms of hardware. Typically an extra register for you. Not much. Okay? But it allows you to basically support an infinite number of devices, because all of a sudden each device can basically say different things. Obviously, if you're sharing and you're pulling all like 10,000 devices, then interrupts no longer make sense. But luckily, nobody really runs 10,000 devices on a single machine. I mean, nobody does that. And this is how the interrupt flow works. So you have 2 devices. They share the same IRQ number. Okay. You basically go to the PIC, which is your interrupt controller. Okay. And then the interrupt controller basically checks on each device. Okay. And once it knows which device is the one, will basically go to the actual interrupt of that device and then run the actual handler. And once you run the actual handler, you have done the most important parts of the work already. This is your interrupt vector table on Linux. So you have from 0 to 19 non-maskable interrupts and exceptions. These are basically 19, the only 19 that you should basically hopefully use the do not share flag with. Okay? Then you have a bunch that Intel has reserved for whatever co-processors that it has and different things. And then you have basically different numbers for different interrupt types. So external interrupts that are coming maybe from USB or from your camera or something. You have numbers, then you have system calls, then you have again external interrupts, and the list goes on. And then there is like even some that are for future use. Maybe Linux evolves into something different, so they have kept like a bunch temp for themselves. Okay. So how do you implement an interrupt handler? You have the hardware, you generate an interrupt, okay? Goes to the interrupt controller, goes to the processor interrupts the kernel, do IRQ, is there an interrupt handler for this? Okay, it's either yes or no, so do you have a registered device already or not? If not, then you just like, exit. If yes, then you go and run the interrupt handler. Okay? So for synchronization purposes that we're going to actually cover, hopefully the next time we talk about Linux, if we ever do that, there are ways to actually mask interrupts on a single processor. In a multi-processor system, you might have 8 cores or 10 cores or 12, I don't care, right? Each one of them will have its own interrupt handlers. There used to be a way in the old days where you just internally inside the kernel would call a single line that would basically stop all interrupts on all processors. Now, if you have lots of people using that to basically gain maximum, I want maximum speed, I want my device to look flashy and nice, give you the best output, then if you have people basically masking interrupts all the time in their device drivers, then your computer is basically useless, right? So Linux basically pulled that out. It used to be like that. So now there's no global way to do that. So if you're building a device driver that actually deals with multiple processors, as a device driver developer, you need to actually start thinking about synchronization between the different co-processors or the different processors on the chip. Okay? And Linux gives you ways to do that. Some of them is basically synchronization mechanisms, locking and semaphores and these very nice, lovely things. But also it gives you some of these calls that are internal to the Linux system, to the Linux kernel, that you can actually use to enable some IRQs, disable them, and so on. Bottom halves. Okay? So now that we have covered the most important part of your interrupt handler, now what actually does the work, it comes at the bottom half. This is basically where the actual driver is implemented. Okay? You should offload as much of the work as you can to the bottom half. And that's basically because good drivers should make your computer work, not make it slower. Now, when you're writing your bottom half code, you should know that this is basically a promise to run rather than a time to run. So when you are implementing things in the bottom half, that means that you cannot assume any synchronization or when it will run. I don't know, the processor doesn't know, the kernel doesn't know. I mean, it will just run when there's time for it. However, typically what happens is that right after you exit the handler, which is the most important part of the code, where when you have all your interrupts masked and so on, you actually start running your bottom half of the same code. Okay? But then all interrupts are enabled back. So this is how we, I mean, there are no magic rules for this. Nobody actually checks behind you, the people. I mean, there are tons of drivers being written every day, but this is what you should keep in mind. If the work is time sensitive, it goes in the top half. If the work is related to the hardware, it goes to the top half. If the work needs to ensure that there are no other interrupts that are interrupting that work, it can go to the top half, because you can also do other things. Everything else should go to the bottom half. So in our network example, everything that we said should be in the top half. Everything else, like processing the packets, actually doing TCP/IP, or whatever protocol that you're using, should go in the bottom half. Okay? And there are no single way to implement bottom halves. There are actually at least 4 different ways to build the bottom half in your Linux kernel. Okay? All days, people actually had something that they called the bottom half. It's actually a technique that is called the bottom half to implement the bottom half. But that was until kernel 2.3. Then they started evolving. The way that the old bottom half worked is that it had 32 predefined, well-defined bottom halves that you can only use. It basically means that, you know, people back then thought that I need hard disk, I need memory, I need mouse, I need screen, you know, a bunch of devices, and that's it. So we needed more than 32 bottom halves, and this quickly became a bottleneck. So they started building these different mechanisms to actually improve the system. The first one was task queues. It's also dead. Okay, so this is their first answer to the bottom half not working. And the idea was that you define a family of queues, sort of quite similar to the priority queues that you had in the scheduler in Linux, but now for interrupts. So you had a family of queues, basically, a bunch of queues with some priorities, and the kernel would go into each task queue. They were doubly linked lists. And basically, it will go through the queues and start queuing things one by one, okay, based on their priority. Again, this became a bottleneck in terms of how the system was performing, because for example, for networking, it cannot work that way with 10 gig cards, even 1 gig cards. It cannot work that way. You cannot just have a task queue that you have things as packets come, they get tasks and so on. So now this is replaced by something that's called word queues. The two methods that most of the bottom halves are implemented in today are soft IR queues and tasklets. Soft IR queues is both of them are introduced in kernel 2.3. Completely removed bottom half, that very old system, in kernel 2.5. Soft IR queues basically says that there are 8 bottom halves, not even 32, just 8. Okay? And these 8 are defined, statically defined. You can add one if you want. I mean, the book has like multiple ways to add the soft IR queue, but at the end of the day, nobody does. Okay? And that find ways to do the bottom half. On top of that, there's the tasklets. Soft IR queues can run in parallel. The same soft IR queue can run on 2 processors together. So it does not provide you with even any synchronization or anything, it just runs. Okay? Now, tasklets are implemented on top of soft IR queues. They actually they use 2 of the numbers of soft IR queues because soft IR queues also has a number table. Okay, so they have 2 numbers. One of them is for high priority tasklets, one of them is for low priority tasklets, and they run they're an implementation on top of the soft IR queue. So as everything in computer science we do, more encapsulation solves some problems, right? So we encapsulate the soft IR queues in the tasklets. Soft IR queues are used when the performance is totally, important. So networking subsystem, it has its own predefined soft IR queues. So this is a time summary of how things evolved. So you had soft IR queues in version 2.3. Word queues, we'll talk about them, were introduced in version 2.5. But then these 2 were decommissioned in version 2.5. And in terms of performance versus ease of use, so you have very high performance for soft IR queues. They're completely built and designed for basically the absolute fastest. You have tasklets in the middle, and then you have word queues, which are just super easy to use for implementing your driver, but they are less performing. There is another way that's called threaded interrupts. We're not going to go through that much. Threaded interrupts is basically a way that basically says that, you know what, instead of even trying to implement the bottom half and the top half and everything, your top half is just acting, basically sending an acknowledge, and then clearing the hardware, okay? And then everything else is implemented as a kernel thread. So if you have everything as a kernel thread, then what happens? It gets scheduled as a kernel thread. So all of a sudden you have this system that basically enables you to write an entire device driver by just writing normal thread without thinking about top halves and bottom halves. We'll not cover it more in the lecture. So as I said, there are only 8 soft IRQs, and these are 0 for high priority tasklets, 1 for timers, 2 for send network packets, 3 for receive network packets, 4 for block devices, which is basically your hard disk, 5 for normal priority tasklets, 6 for the scheduler, 7 for high resolution timers, and 8 for RCU logging. These are the only 8 IRQs that are defined. Typically, you only go for the soft IRQs. You only deal with them as a programmer, as a kernel developer, if you're working on the network subsystem or on the I/O subsystem. Okay. So as you said, soft IRQs are for high frequency and high threaded use because you can run them in parallel also. So you might be able to process multiple packets, multiple buffers worth of network packets on different processors in parallel, and use tasklets for everything else. Okay. As everything is defined in the kernel, there's a tasklet structure that basically has all the tasklets linked together. And this is actually the definition from the code. So you have basically something that points to your next tasklet. You have the state of the tasklet, which can be basically if it's scheduled, for example. So if a tasklet is scheduled running, if you have multi-processor systems, it will read that flag and see if, oh, it's already scheduled. I should not try to schedule that tasklet because it's already running somewhere. Okay, and as we said, tasklets cannot run on 2 processors at the same time. You have the count, and you have also data that the tasklet can use. This is actually basically what each field in the tasklet structure means. Okay, so I think the only one that we did not cover is the count, which is the log counter, and func is basically the pointer to the actual handler. Now, if there are too many, so since 8 tasklets are implemented as soft IRQs, so in essence they are soft IRQs. To the kernel, they are soft IRQs, right? Now, each soft IRQ has its own handler, so if you're going to the high priority tasklets, then the kernel will do something, and that thing will be basically go through the tasklet struct, and basically go through them one by one, okay? However, it can be the case that you have lots of input coming in from soft IRQs, and the kernel cannot just cope with all of them, okay? So if there are too many soft IRQs, you can end up basically, again, hogging the entire system and not doing anything, right? Because again, when you finish an interrupt handler, you can go to you go directly to the bottom half. The sad thing also is that many of these soft IRQs can call themselves. Basically meaning that a soft IRQ can basically, if there's more data, for example, the network buffer can just recall itself. So it can start from all over. You have a question?
Yeah. So I was just wanted to know the soft IRQs, are they sort of written in assembly and they're like architecture specific, dependent?
No.
But are they written in assembly? And
I mean, there are definitely parts which are written in assembly, but most of it, no. Nothing is written. Almost nothing is written in assembly.
okay, so it's like architecture independent.
Yeah, because it's basically, I mean, the whole idea is that you have, so for example, the high tasklet IRQ, a soft IRQ, it basically goes through a structure and goes through each tasklet and tries to basically do the bottom halves for all the different interrupts that already occurred, right?
Mm-hmm.
The block devices again, what it's trying to do is basically trying to read from a block device, right?
Yep.
Most of it is going to be just like moving data and pointers and stuff. A little bit of it can be device independent, but that's very little, if any. Okay. So kernel soft IRQs is basically the way of the kernel to basically stop the system from getting completely overrun by all the soft IRQs that are happening. The way it does that is that it takes, it's like the threaded the threaded IRQ I was talking about, but what it does is that it basically takes some of these tasklets or some of these soft IRQs and converts them into kernel threads. And if you convert something into kernel thread, then it gets scheduled at whatever time. It's no longer an interrupt handling process. It's more like as if there is a user process that is running and you just need to run it. And it runs actually with the lowest possible priority, which is 19. So basically, you take these bottom halves and you even run them with the lowest possible priority. And that is typically what happens when you press a key and then press another, and your computer is completely hooked. And then you see the letters coming, like, you know, and like after 2 seconds or something. It's basically it's being overrun by soft IRQs, so it just goes to key soft IRQs. Okay, so it's kernel optimization. So the last thing is work queues. And this is a different way of deferring work. And what it does is basically, there are many of these kernel soft IRQs, and there are many of these soft IRQs, there are many devices that need to sleep. Okay? Now, soft IRQs and tasklets are not built to sleep. They're built to basically have some parts of the interrupt being completely run from A to Z with no sleeping. However, if you're fetching data, if you're reading from disk, you actually need to sleep because you need to wait for that anyway. So the way that the way that work queues work is that they actually take any bottom half and convert it into a kernel thread, and then these kernel threads can just sleep whenever they're ready. They just, you know, they go through the normal process. It's basically blocking on I/O. So you can't block on I/O and sleep and wake up and do all sorts of things as if it was a normal kernel thread. The way it does it is that it actually implements a special kind of thread that is called a worker thread, which is, there is one worker thread per each processor. Okay? The worker threads are again threads, they're just special threads, and there can be only one of them per processor. Okay? And this is how this very nice architecture looks like. So you have basically, for each processor, you have worker thread, okay? And for each processor, you have a per CPU work queue struct that basically has all the things that are now scheduled or going to be scheduled on this core. And then you have basically, you can theoretically create other worker threads, although the system does not do that by default, but you as a programmer, for some reason, you can create a worker thread. So actually in the book, he gives an example by basically saying that I'm going to create another worker thread that I'm going to call Falcon. Okay, but that doesn't make any sense and nobody does that. So in theory, you can have a work queue structure that is one per worker thread, but usually there's just one worker thread, so these will be almost the same. And then you have, for all the bottom halves that you're going to schedule, you have a structure that basically links all of them together. Now, one of them will get scheduled to the first worker thread, the second one will get scheduled to the second worker thread, and so on. So you have a list of all, and the list per processor, and the worker thread per processor. Is that clear? No? Yes? And then, since there's this mess between the bottom half, now you have soft IRQs, you have tasklets, you have worker threads, and or you have work queues, and you have whatever other things that you're going to use for the bottom half. There is a deep need for being able to lock for on some of the data that these things are dealing with, because the same parts of the same interrupt can be handled in different ways. So parts of it will just be like the normal interrupt handler. Parts of it will just go on, do software IRQ or key software IRQ. Parts of it can be a work queue task. So this is the end of the lecture. I hope I did not bore you to death. Thank you. Any questions?
So I had a question about, you said that the drivers, they are in atomic context, and so like the atomic context, like how is it actually enforced?
The top, the top half should be atomic. Basically, it should all run. Well, if you have all interrupts not enabled, then it will just run all of it together, right? And this is why you want the top half to be very short.
Okay.
So by atomic context, I mean it's atomic now if you enable all the other interrupts except for your same interrupt type. It's atomic in the sense that your same interrupt type is not going to override you, right? But if your network card, which is very different from your keyboard, is going to do something, then you don't need to actually do any locking between them, because you might be streaming something while you're pressing your keyboard.
Okay. And like the top half and the bottom half, are they like just like modules, or like are they like connected, as in how are they sort of?
So the top half schedules the bottom half.
Okay.
So the top half does all the sorts of like acknowledging, and then after acknowledging it clears the hardware and so on, and then it schedules the bottom half.
So it's like one process.
Yes.
Governing the other process.
Yes.
Okay. Thanks.
Okay. Thank you.